Hello everyone, this is the second video I prepared for you in order to explain the solution of some questions I provided during the tutorial sessions. Again, I selected the questions based on the feedback I received from the students, and based on my experience that it is necessary to know how to solve the problems related to control systems. In the first problem, we are looking for the final time response of differential equations given here. This is a set of first order differential equations. We would like to find time response of y1, function y1, and function y2. As I mentioned in my previous tutorial sessions and in my previous micro video, in order to solve the differential equations, we need to take Laplace transform of differential equations. If I get the Laplace transform of the first differential equation, I have sy1s minus y10, which y10 is initial conditional function yt, plus y2s equal to 2s over s squared plus 1. S over s squared plus 1, in fact, is the Laplace transform of cosine t according to Laplace transform table. And for the second one, I have y1s plus sy2s minus y20, which y20 is initial condition of the function y2t, equal to 0. If I apply the initial condition to the system, I have y10 equal to 0 and y20 equal to 1. If I rearrange the first algebraic relation, I have sy1s plus y2s equal to 2s over s squared plus 1. And for the second one, I have y1s equal to 1 minus s y2s. Again, as I mentioned in tutorial sessions, the beauty of using Laplace transform for solving differential equation is that we transform differential equations in time domain with simple algebraic equations in Laplace domain. So to solve these two algebraic equations, first I just substitute the value of y1s in terms of y2s in the first relation. By substituting that one, I have s multiplied to 1 minus sy2s plus y2s equal to 2s over s squared plus 1. If I rearrange the relation based on y2s, I have minus s squared minus 1 y2s equal to 2s over s squared plus 1 minus s. If I get the common denominator for these two items, I will have 2s minus s cubed minus s over s squared plus 1. Again, I just factor out s from this one. In fact, here is minus s cubed plus s. I factor out from it. And as you see, in both sides, I have the item minus s squared minus 1. These two items cancel out each other. So y2s will be equal to s over s squared plus 1. Since we are interested to find the time response of y1s as well, so I just substitute the value of y2s in this relation, the relation given here. By substituting y2s in this relation, I will find the value for y1s. So the value for y1s will be equal to 1 over s squared plus 1. So I have the function of y2s and y1s. By taking the Laplace inverse of these two, I see that the Laplace inverse of y2s according to the Laplace transform table is cosine t, and the Laplace inverse of y1s is sine t. So we easily find the solution of this set of differential equation using the Laplace transform. And now we know that the y2t is cosine t and y1t is sine t. In the next problem, again, we are interested to solving a second order differential equation here with the initial condition, or when all initial conditions are 0. Again, to solve this differential equation, second order differential equation, I take the Laplace transform of this differential equation. By taking the Laplace transform, I have s2ys minus sy0 minus y prime 0, which y0 and y prime 0 are initial condition of the yt, plus 9ys equal to e minus s. E minus s is the Laplace transform of delta t minus 1 according to, again, Laplace transform table given in lecture. So by applying the initial condition y0, 0 and y prime 0, 0, I can find the relation, the final relation, s squared plus 9 y of s equal to e minus s. So y of s is equal to e minus s over s squared plus 9. So what I do is that I just multiply here I have in numerator coefficient 1 in order to reshape this fraction, in fact this fraction. In terms of sine Laplace transform, I just multiply the denominator by 3 and 1 over 3. The theorem that we need to use, and it is important to know, is the second shift theorem. The second shift theorem says if Laplace of f of t, function of t, f, in time domain is f of s, then Laplace inverse of e minus as f of s is equal to ut minus a ft minus a, which ut minus a is a shifted unit step function. Now, I know the Laplace of 3s squared plus 9 is sine st, sine 3t. In fact, sine 3t is my ft, and 3 over s squared plus 9 is my f of s. By considering and applying the second shift theorem, I see that the Laplace inverse of 1 over 3 e minus s, 3 over s squared plus 9. Here 3 over s squared plus 9 again is my f of s, and e minus is my e minus as. In this case, a is equal to 1. So by applying the second shift theorem, I see that the Laplace inverse of this function, the function y of s, will be 1 over 3 ut minus 1 sine 3t minus 1. One thing you need to consider and keep in your mind, because we have the shift here, the t minus a is applied in both ut minus a and ft minus a. Here again, if my ft is sine 3t, ft minus a or ft minus 1 will be sine 3t minus 1. So this is the important points that you need to keep in your mind. Actually, the purpose of this problem is to help students to understand the use of second shift theorem and applying it on a given function. In the third problem, we are looking for a simplified transfer function of, or a simplified transfer function between output and input. As shown here, we have the block diagram here. We would like to simplify this block diagram. To simplify this one, if you look at this block diagram, we have a negative feedback loop and we have two feed-forward routes. So for the first negative feedback route, if you look at again at the lecture note, the simplified transfer function of a negative feedback loop will be g1 over 1 plus g1 g4. Again, here we have plus, since we have a negative feedback loop. In the second one, we have just two parallel routes. Keep in your mind, here we don't have a loop, just they are two parallel blocks. So in order to simplify these two, because they are parallel, the simplified transfer function of these two routes, it is just the summation of these two, g3 and g2. So the resulting transfer function for these two parallel routes will be g3 plus g2. So the simplification of the simplified version of these two blocks will be here g1 over 1 plus g1 g4 is the simplified feedback loop, and g3 plus g2 will be simplified simplification of two parallel routes. Here again we have two series blocks. We can further simplify these two blocks by just multiplying these two transfer function of these two blocks. So the resulting will be g1 over 1 plus g1 g4 multiplied to g3 plus g2. Now at the final stage, we just need to substitute the value of g1, g2, g3 and g4 in this transfer function. By implementing the values in this transfer function, we will have the final transfer function as g of s equal to 2s plus 1 over s multiplied to s plus 3. So the purpose of this problem is that to familiar the students to how to use the simplification rules for the given or complex block diagram. In this last question, we are looking for the output response of a given transfer function subject to a unit step change of the input in the input, and we would like to see if the system is stable or not. We would like to find the gain of the system, and we would like to see whether the system is under damped or over damped. First, I will look at the stability of this transfer function. In order to see if the system is a transfer function or a system is stable or not, we need to look at the roots of the poles of the system or poles of the characteristic equations. By finding the poles of the characteristic equation, we see we have two simple roots, one s plus 2 and s plus 1, which both of them are negative, and they are in the left hand side of the complex conjugate plane, complex plane. So we have two negative poles both in the left hand side, so the system is stable. And again, keep in your mind, if we have two roots, if all roots of our transfer function are in the left hand side of the complex plane, the system is stable. If we have even one positive roots in the right hand side of the complex plane, the system is unstable. If we have the roots on the simple roots on imaginary axis, the system is critically stable. Here, because we have two roots on left hand side of the complex plane, it means the system is absolutely stable. Now I'm looking for to see whether the system is under damped or over damped. The general format of a characteristic equation of a second order system is in the form of s squared plus 2 zeta omega n s plus omega n s squared, where zeta is the damping ratio of the system and omega n is natural frequency of the system. To see, before saying that this transfer function is over damped or under damped, I define the definition of the under damped system. A system is under damped if damping ratio of it is bigger than 0 and less than 1, or if it has two complex conjugate roots. Otherwise, the system is over damped if its damping ratio is bigger than 1 or if it has two real roots. Using this criteria, justifying the characteristics of the system based on its damping ratio, I just need to compare this general format with this characteristic equation. If I compare this characteristic equation with this general format, I see that my omega n squared is 2 and 2 zeta omega n is 3. So in the first one, I calculate omega n, which it will be equal to roots of 2, and then omega zeta or damping ratio will be 3 over 2 omega n, or equal to 3 over 2 roots 2, which its value is bigger than 1. So it means that the system is over damped. I can justify the characteristics of the system based on the roots of the system as well, since again we have two simple roots, and according to this definition, the system is over damped. Since the system has two real roots, it is over damped. Now I will look for gain of the system. The gain of the system is the value of transfer function when s is equal to 0. So simply I just need to put the all s of the transfer function equal to 0 in order to find the gain of the system. By putting s equal to 0, I see my gain will be equal to 1 over 2. In the next question of the problem, we are looking for to see or to sketch the time response of the system. In order to plot or sketch the time response of the system, the most important thing is we need actually to check different things. The first one, we need to check if the system is stable or not, which we did already, and the system was stable. Again, because we have the second order system, we need to see that if it is over damped or under damped. Again, we check it, and the system was over damped. And at the last step, we need to find its final value. In order to find the final value of the system, we need to use the Laplace, we need to use the final value theorem. Before using the final value theorem, we see that the y of s is equal to gs us, and since the input is a unit step, the y of s, the y of s will be, function of y of s will be equal to 1 over s squared plus 3s plus 2 multiplied to 1 over s. In order to find the final value of the y of s, I will use the final value theorem. The final value theorem says that limit of y of t when t goes to infinity is equal to limit of s y of s equal when s goes to 0. So by applying this theorem, I will see the limit of s y of s when s goes to 0 for this case will be limit of s multiplied to 1 over s squared plus 3s plus 2 multiplied to 1 over s. This s will be cancelled out with this s. When s goes to 0, the final value equal to 1 over 2. Here you see the sketch of the response. As you see, the final value is 0.1 or 1 over 2. And since the system is overtime, we don't have any oscillations. And the response of the system is almost the same as the response of a first order system. I hope you find this presentation useful for preparing yourself for the midterm exam. If you have any further questions, just feel free to come to my office or send me an email or ask your questions during the tutorial session. Have a good day and see you next time. Bye.